I'm Xiaodong from Intel, and my presentation name is New Typing Technique to Reform Erasure Code Data Overwrite. In this topic, I will first look back on Erasure code about data creation, and the first I will look back on the traditional Erasure code encoding. Then I will explain the theory about the new Erasure code encoding, which also can be named Refraction-encoding. During that time, I will list the benefit of Refraction-encoding over traditional encoding. Second, I will show you the relationship between block storage and Erasure code. Then I'm going to talk about how to apply Refraction-encoding to data creation. In the end, I will discuss on how to apply Refraction-encoding to block storage. So, Erasure code is a data protection method widely used to guarantee data reliability for cloud or distributed storage. Operations on data includes creation write, overwrite, and read and delete. For recovery, for redundant data, we have an actual operation that is recovery. Of course, when you read or delete data, you don't need to do any Erasure code calculation. But so among these operations, data creation, data overwrite, and data recovery, these three operations need to do Erasure code calculation. So these three operations are the workload of Erasure code. When using Erasure code, data will be broken into several data slices, and these slices are encoded to get parity slice. The number of parity slices and the number of source data slices are configurable. Source data slice is also called source vector, abbreviated as D, and parity slices are also called parity vectors, abbreviated as P. Compared with multiple replica method, Erasure code saves lots of redundant storage space while keeping a same or higher reliability. Here, this statement is a general description on Erasure code. Here we call it traditional encoding. First part of this presentation, we will use Erasure code 6+3, which has 6 source vector and 3 parity vector. The first formula is used when create data, and the second formula is used to do data overwrite. And the diagram is the status of data overwrite. From diagram, you may find if only one source vector is changed, all the parity vector also need to be changed. This a bit of overwriting leads to corresponding parities change. It is overwrite penalty. More than that, what we use to carry on the overwrite process is the second formula, which will lead all the vectors and the whole encoding matrix involved into the overwrite process. Let's come to the next page and explain the penalty details. The data flow is shown in figure. When quoted D0 is coming to the storage node. Storage node A need to read out D1 to D5 from these storage nodes. In order to get the new parity nodes, storage A need to do the parity generation calculation with quoted D0 and D1 to D5. In this solution, all nine nodes are required to participate into the calculation. So the number of storage nodes involved is 9. Number of vectors transmitted in the network is 9. Number of disk operation, for example, disk read is 5, disk write is 4. And all the computation is accumulated in storage node A. The whole computation cost includes 18 XOR operation and 50 multiply operation. So how to optimize above cost parameters for data overwrite in order to reduce the network computation and disk workload? Refraction-encoding is raised to optimize them. It has been mentioned a few times before. Let's talk about what is usually called refraction-encoding. To get a better understand, I take an image as example. In this example, planning to store this image by usual code 4+3. In order to do this, we need to split this image into 4 slices. And from the parity generation formula, parity is gotten by cumulative overlay by the data slice. That is to say, in usual code, parity is cumulatively overlaid by data slice. Later, style of slice 2 is changed to get a yellow background. So what happened to the parities? We can get each parity by 2 steps. Step 1, we need to extract the previous slice 2, and step 2 is to insert the changed slice 2 into the overlays. So we can get a new parity by replacing changed data slice. In mathematical point of view, new parity coded PL is equal to previous PL minus previous data and the new data. Since in Java field, minus and 8 are all XOR operation, so we can get the PL from the difference of changed data and the previous parity. This way is Erasure code refraction-encoding. It is derived from the data overwrite situation. For Erasure code, K is the number of the source vector, and W is the number of parity vector. Based on that example, as opposed to the traditional encoding formula, a standard refresh encode formula is a set of equations. In this set of equations, M is the index of changed data. D and P are the previous data and parity. Coded D and coded P are the changed data we will get. Alpha, beta, and omega, and so on are the coefficients extracted from the encoding matrix. This expression is derived from data override situation, so of course, it is naturally effective in data override situation. Let's check its workflow for data overwrite. The storage nodes receive the new data. After that, here is 4 steps to do the workflow. First step is to get a difference by XOR between new data and previous data on the change. And the second step is to replace source data vector. Here, we will replace dn with coded dn. And step 3 is to splice the difference to all the parity nodes. Step 4 is parity nodes to refresh the difference into their parities. With the new workflow of EC overwrite, let's check its cost. Number of involved storage nodes involved is 4. Number of vectors transmitted in the network is also 4. Number of disk operations, for example, disk read and write, are all 4. The computation is not cumulative in only one storage node. It is distributed to the parity nodes. So the computation cost is only 4 XOR operation and 3 multiplication operation. Here I list the comparison table on some typical Erasure code between traditional encoding and Refraction encoding. It is about the computation network and disk workload. Before the data side, for 6 plus 3, we have detailed explained. From the comparison, overhead of Refraction encoding is much less than the traditional EC encoding. And from the comparison of data site or data strategy 9 plus 3 or 12 plus 4, whose source vector number is much larger than the parity number, Refraction encoding is really helpful to doing data overwrite. After introduction of Refraction encoding, let's review the workload of Erasure code. For data recovery, the traditional EC encoding is unavoidable, and for data creation, traditional EC encoding is also applied. But for data overwrite, we can use the Refraction EC encoding instead of the traditional EC encoding. In object storage service, Erasure code operation granularity is the whole object. So the size of an object is commonly larger than megabyte, so it is easy to do to cut the object into slices and encode this slice within the object itself. But in block storage service, things are different. At the start, the content of the volume is totally empty, and its storage process is not only one operation, but a lasting process with random block write, step by step. During this procedure, the volume is filled here and there, so there are always a lot of empty holes inside the volume. For example, for this new created volume to provide block service, at the first time it is all empty. After a while, some blocks are used, and it starts to have some content fragment. As time goes by, random blocks are written and the fragments are more and more, but there is always no proper time there is no proper time and position to segment the whole volume and do the Erasure code encoding. Here we have a volume which is provided by block storage service with Erasure code 4 plus 3, who has 4 source data vector and 3 parity vector. The block size of this volume is 4 kilobytes. Now one data block is coming, but how to do the Erasure code work? Here we took 2 traditional methods to make comparison. Here. Method 1 is also called block self-encode. In this method, typically operation granularity is the whole 4 kilobyte block. This block size is too small to encode by itself. And when doing this 4 kilobyte block random write, encode each data slice will be only 1 kilobyte. And the system efficiency will be very low since all the data size will be 1 kilobyte through network and disk. Second possible method is waiting other incoming blocks and treat other coming blocks as is EC strap companion. If you encode one block with other incoming blocks, metadata will be large and hard to optimize since each block random rate, each coming block has no relationship with each other. So we should add metadata to record the relationship of each block and record their storage and record their storage position. So let's start to apply refresh EC encoding into data creation. The example is still Erasure code 4 plus 3. Block A, B, C, D. Here, block A, B, C, D are belonging to one EC stripe group. They share three same parities JKL. At the start, their positions are all empty, so you can't see any ABCD. And block A is arriving first. When writing block A, we just store it to its storage position and copy it to the parity positions. When writing block B, we also store storage block B to its storage position, and since the parity position is not empty, so we need to multiply B with different coefficient and XOR the products with the content of parities, and in order to refresh the parities. When block C and block D is coming, the operations is same with block B. So the Erasure code is becoming here 3 and 3 plus 3, and in the final the Erasure code will become 4 plus 3. In this method, every block is encoded timely. Its encode process is only related to itself and the parities. Every time writing a block, there are always only 4 storage nodes involved into the process. Erasure code computation is distributed to the parity nodes. And so this way, every Erasure code operation, no matter data creation or data overwrite, is in block line size. Operation latency of creation and overwrite is same, so the latency is stable. Since no need to wait in EC stripe companions, it has timely reliability. So let's review the workload of Erasure code. For data recovery, traditional EC encoding is still unavoidable, but this time, refresh EC encoding is not only applied in data overwrite, but also in data creation. From this page, let's try to apply refresh EC encoding to block storage. First, create a simple mapping relationship between logic blocks and the physical space. Let's still use Erasure code 4 plus 3 to describe it. Blocks of this volume are divided into different segments, and most continuous blocks are in one block segment. So in the figure, this volume is divided into 4 segments: segment A, segment B, segment C, and segment D. In order to decrease the quantity of metadata about the Erasure code stripe groups, 4 volume segments are placed in 4 storage nodes. Simultaneously, 3 redundant segments are placed in another 3 storage nodes as Erasure code parity pairs. From this figure, you may find that data blocks with a same index of size inside every storage node share same parity block. For example, all blocks in stripe C, all blocks with offset with index offset C share same parity block. They are belonging to a same stripe C, and they can be used and they can be used to recover themselves. When a data block whose index belonging to storage node A is first written, since its corresponding companions are all empty, so we just store that block into storage node A and also copy it to its parity positions. When writing two sequential blocks whose index belongs to storage node C, this time here we store two continuous blocks in C. Parities for block in stripe B is empty, so we just copy block B into the parities. And for the parity in stripe C, since the parity is already written, so we need to multiply this block with different coefficients and XOR the product with previous data to refresh the parities. When writing two sequential data to storage node D, the operation is same with this operation. We need to just copy the block in stripe D. In stripe D to its parity positions, and for its first block in stripe C, since there is already have parity data, so it also need to multiply with different coefficients and XOR the products with previous parity to refresh them. And this time you may see stripe C is erasure code 3 plus 3. After a long time running, volume data segments and parity segments look like as shown in this figure. There is a single block random block writing and also sequential random block writing. Blocks between A, B, C, D has no relationship with each other unless in the background they share same parity segments. And the blocks of straps are full of. And this table is the relationship between source and parities in the diagram shown here. You may think that blocks of straps are full of data. Their parity contains the information of the blocks both in A, B, C, D. So in this strap, the erasure code is 4 plus 3. And for strap B, D, and G, it has only 4 blocks. So the parity just contains the information of 3 blocks. And for these three strap, the erasure code is 3 plus 3. Strap E has 2 blocks, data AE and data DE. So its parity has only 2 block information. So for this strap, its erasure code is only 2 plus 3. For strap A and strap H, since there are only 1 block in this strap, so you can treat them as replica method, or also treat them as erasure code 1 plus 3. As time goes by, the user continue to use this volume to the volumes blocks are full of data. The volume will be full of erasure code 4 plus 3. So the volume is totally a 4 plus 3 erasure code. So since there are some contradictions of erasure code, for example, the storage space versus redundancy, the replica method versus parity method, and for the operation may be an emergent operation, or the operation is a gradually operation. Because of the existence of this of these contradictions, it is not the end of refraction encoding. And that's all. Thank you. Any questions? Oh, thank you.